Today we continue with the topic on coastal littoral processes. We'll begin by looking at sediment budget, which is the quantification of source, sink, and transport of sediment in a selected segment of the coast over a specific time. The purpose is to determine soil loss and thus the need of replenishment, and also to identify favorable or unfavorable littoral processes. Assuming this dash box here on the figure is the coastal region from the landward limit to the seaward limit where active littoral processes takes place. Using the concept of sediment budget, we will be interested to find out what is the material influx, the amount of material that enters into this domain, and the material outflux, which is the amount of material that exit from the domain. Meanwhile, within the domain itself, sediment transport takes place, but part of the sediment may be settled and is no longer in suspension, although settled material may also be resuspended or be permanently deposited. So by working out the total influx, outflux, and deposition, we will be able to find out what is the total amount of sediment in this domain. Here we look at the same domain but looking from the top. As we mentioned earlier, from the land side, we have material influx, which may be attributed to erosion from the cliff or dune in the backshore. It may be erosion from the beach itself. It may be sediment contribution from rivers that enter into this littoral zone. But meanwhile, from the littoral zone itself, it may also deposit sediment to the dune and the backshore. It may deposit sediment in the lagoon area, for example. And wind also may cause the exchange of material in and out of the littoral zone. Whereas on the seaside, sediment may be lost beyond the offshore wave breaking point. It may be lost by dredging or other processes such as calcium carbonation, where it involves the formation of the coastal reefs. Now, one thing not to forget is, of course, the longshore current, which may also be contributing to the material influx and the material outflux. On this slide, we explain some of the sand sources. And on this slide, the sand sink. Sink meaning how the sediment may be lost from the coastal littoral zone. This figure here shows a simple calculation of the sediment budget, whereby we quantify the inputs and the outputs, which basically are the material influx and outflux. For example, over here we have longshore influx from here at 50,000 meter cube per year. We have cliff erosion influx at 5,000 meter cube per year, and we have onshore transport of 5,000 meter cube per year. Meanwhile, we have output due to longshore transport here, negative 55,000 meter cube per year from this part of the coastal zone, and we have offshore transport at negative 15 meter cube per year, which means loss beyond the breaking point. So combining the influx, the positive components, and the outflux, the negative components, we find that overall this segment of the coastline experienced a net loss or net erosion of 10,000 meter cube per year, negative 10,000 meter cube per year. The negative sign indicate loss, indicate net erosion. This is another example. The dash box here is the area that we are interested in. This is the seaside with dominant wave direction from here. This line represents the offshore limit. We have the mean low water line and the mean high water line. We have the coastal cliff and the higher boundary of the coastal cliff, and we have the landward limit. The segment of the coastal line considered here has a width of B. This domain here received material influx due to the cliff erosion, and it also experienced material outflux to the offshore region. Meanwhile, it has longshore transport influx from this side and longshore transport outflux to this side. And as a result of the dynamics, the cliff of the coastline here undergoes changes. Here we show the first survey profile and the second survey profile, where a recession of the shoreline was observed. This is our limit on the land side, and this is our limit on the sea side. So presuming that these are the values corresponding to the littoral processes of this coastal region, we have Q4 influx of 100,000 meter cube per year, which is the longshore transport here. We have, in small letter, Q2 plus of 1 meter cube per year per meter, which correspond to the cliff erosion here. So for every meter of the cliff, we lost 1 meter cube per year. So we will have to multiply that by the length of the cliff in order to get the total sediment contribution from the cliff erosion. So the small letter q is in terms of meter cube per year per meter, whereas the capital letter Q is in terms of meter cube per year. Likewise, in terms of the loss to the offshore limit, we are given the information in terms of small letter q of 0.5 meter cube per year per meter of the coastline, and B is given as 10,000 meter or 10 kilometers. So we can apply the sediment budget concept by summing up the sources and the sink and work out what is the net changes in this domain. In this particular case, the influx from the cliff and the outflux to offshore is given. The influx from longshore transport is given, and the example here assume that the total sources and the total sinks are balanced. So we have sum of source minus sum of sink equals to 0. So we are using the equation to find out how much is the longshore transport outwards here. So we find the solution to be this value. Now take note in this example that there is an erosion of the coastline, which is already mentioned here, which is given as 1 meter cube per year per meter of the cliff is being eroded. But overall, the erosion here and the loss to the offshore and the longshore transport in and longshore transport out are balanced. So the sum of source minus sum of sink equals to 0. So if we inspect the numbers more carefully, then we already know that there's a cliff erosion here. If we compare the longshore transport, then we found out that what is going out here on the right is more than what is coming in here on the left. So which means that we have net loss in the longshore transport direction. And also we have net loss in the direction offshore. So which means that practically this section of the coastline is experiencing net erosion. In our earlier examples, we looked at how we apply the sediment budget equation to analyze quantitatively the erosion in a particular segment of beach. Here we look at a slightly different example of how we analyze the sediment dynamics qualitatively. Consider the hypothetical coastal segment as shown, which consists of a line of eroding cliff from B to D, a river discharging to the coast at point E, and a straight segment of sandy beach from F to H. Also shown on the figure is a spit here at A, a dune parallel to the beach at F, a lake which is connected to the beach via an inlet at G, although the inlet is shown as dashed line. We'll come to that later. And the dominant waves is coming in from this direction, where the parallel lines here show the orientation of the wave crest. We're going to look at how we can analyze the littoral processes based on information as presented. First and foremost, we understand that this cliff is erodable from B to D. So under the wave attack at this angle, we can expect that there will be sediment loss and thus littoral transport from this cliff, which may advance or propagate in this direction as well as this direction. The extent of the erosion that happened at this cliff can be confirmed through the aerial photograph or land survey, but we can also examine specifically the formation of this spit, where the sediment sources are most likely directly from this portion of the cliffs. Meanwhile, for the sediment loss in this direction, they will eventually come to the river mouth at E. Now, all rivers carry sediments, so the sediment from the cliff erosion and also the sediment of the catchment, which is discharged through point E, is going to meet somewhere at the coastal area here. Now we can try to estimate the total sediment discharge from the river by analyzing the catchment soil loss and also the river discharge. We can also make direct measurement in this river. Another way of confirming how much is the total sediment from the river and also that contributed from the cliff erosion is to carry out hydrographic survey in this part of the beach. Now, if the longshore current along this beach is strong enough, of course the longshore current will be developed from this dominant wave. If the longshore current is strong enough, then the sediment will not remain in the river mouth region here and will be washed along this shore. If the longshore current is not strong enough, then the river mouth may undergo sedimentation. If the longshore current is strong enough, then the sediment may be carried along this direction, which means that the sediment sources from the river and the cliff will supply to this beach. So the beach may undergo accretion, it may have increase in sediment, or it may be stable if the sediment sources from the left or from the west side here balance the sediment loss to the east beyond point H. On the other hand, if the material supply from the cliff erosion and the river discharge is not enough, then the longshore transport may actually cause erosion along this sandy beach from F to H. Take note also that we have a dune in the backshore. In order to know whether the dune is undergoing loss or accretion, then we can again examine the aerial photograph or carry out land survey. Over here we have a lake. Usually a lake is not a source of sediment because the water is relatively stagnant and is not moving. Assuming that a pair of jetties is going to be constructed at G to provide access to the lake, then this inlet here may tend to trap sediment, meaning to say that any sediment that try to cross point G here may be washed in and out by the tides, and so instead of the longshore transport carrying them to H or beyond, part of the sediments may be washed into the lake, and this may actually cause the lake to be shallower over time, and it may be more like a shallow coastal lagoon. One last thing to mention is soil loss from the upstream catchment. Assuming that this river carries the sediment loss from the catchment into the coastal area, the amount of sediment may change over time, or it may be relatively steady depending on the catchment development. Suppose that if a dam is constructed somewhere upstream of the river, then a dam may cause the sediment to be trapped in the reservoir, so that the amount of sediment supplied to the coastal area is greatly reduced. So if a project like that is proposed, we need to be aware that the original amount of sediment that arrived at the sea will now become much less, and so that can affect the stable equilibrium of this part of the sea. As we mentioned just now, if the supply from the river and the cliff erosion here is large enough, maybe beach F to H is stable. Maybe beach F to H may undergo accretion, or maybe beach F to H was already eroding. So if the amount of sediment contribution from the river changes, then the whole dynamic of this part of the beach would change as well. So this is an example of a qualitative assessment of a segment of the coast. And of course, all the presumption need to be further confirmed through observation of the aerial or satellite photographs and site measurement and long-term site monitoring.